Okay, so we're going to take a look at some problems dealing with torque. Let's see, so I've selected out some of the more challenging ones because ones where you just kind of use the torque equation outright hopefully are mostly straightforward. So as a brief reminder, torques are found by taking the magnitude of the force times the magnitude of the lever arm times sine of the angle between those two vectors. Now, most of what we deal with is actually going to be 90 degrees, but not all of it. But don't forget about that angle in there in case you're dealing with something where it's not 90 degrees. All right. First one we're going to take a look at, however, using torque and, more broadly, static equilibrium, how we apply torque in meaningful ways. Well, one of the ways that we do that. We've got a setup here that basically says that we've got a balancing act. They've got basically little pillars like this. And what they've got is a stick that is effectively balanced on this. Now, why I say balanced is they've got a weight here. And I do mean weight because the numbers that I've been given are 764 newtons, not kilograms. This isn't a mass. It's 764 newtons. Now, if you do the numbers on that, it's probably about 76-ish, maybe 77 kilograms. That's how we would end up with that. You're welcome to double check. So they're basically giving us the force of gravity on this. That's the force of gravity pulling down on this. And in turn, that is the force. So looking at this object, we have the force of gravity, mg down, which is 764 newtons. But since it is not falling, it is being held up by this force of tension here, which must also be 764 newtons because the object is just sitting there. Well, if the string is pulling up on this block with 764 newtons, that means right here, there's a force applied to the stick downward, also equal to the tension, 764 newtons. Now, what they've also mentioned is they've got a counterweight out over here, but we don't know what it is. They do want us to find the weight. In other words, the force of gravity on this. What they want, honestly, is the force of tension over here. That'll be whatever the weight is holding this up. Now, they've given us a little bit more information. They're calling this one A, that's pillar A, and this is pillar B. And what they've said is find the weight such that the supporting force at A is 0. So what they're actually talking about here, it's a weird way of phrasing it, but it's a perfectly good one, honestly, is that they've got it kind of balanced here like this, and what they really want is if this weight is too light, in other words, non-existent, you could imagine, we could hang something here and we'd have a force holding it up here and a force holding it up here, and then it would stay, the stick would stay where it's at. But what they want is they want a weight over here that counterbalances this one so that we could pull this column out of the way and it would still stay stationary. So we've got a weight here, and we need another weight out over here. Now, one thing that we can bring up at a quick glance, this is a lot like something we've done in class, balancing the stick. We'll find that since this one's close in, we're going to have a large force at a small lever arm, and this is a large lever arm, so we're going to end up with a smaller force. At a glance, while I don't know how much it will be, I'm willing to bet that our weight is going to be less than 764 newtons because of how we balance torques. It's a lot like when we were hanging the masses. A heavy mass close in and a lighter mass way far out could balance each other out based on their lever arms. All right, so basically what they want us to do, if they want the force here to be 0, they're saying basically we want to set it up where we could just move this out of the way and this thing would stay balanced right there with B holding it up. This will be balanced by that, okay? So that's another way of looking at it. And if this is lighter, then the whole thing would tip this way, but column A would actually hold it in place. This is actually pretty similar to a cantilever problem, which is kind of like a diving board, where you have something hanging off the edge. More on that later. But here's what we want to do. Well, we know that we want it where the force at A goes to 0 newtons. Here's the thing. We don't know the force at B. There's going to be a force there, but we don't know it. So we either have to do a whole bunch of extra stuff, or we could do one of the things that we've learned, because we want this to undergo static equilibrium. We want the stick to stay right where it's at, which means our sum of forces are going to have to come up to 0, and our sum of torques are also going to have to come up to 0. Now, if we do our sum of forces, we have 764 down here. The force at B, which we don't know, up here, and we have the weight over here, the force of tension on this thing, down, but we also don't know that. So if we want to go with the forces, our sum of forces would look like this. My sum of forces would be equal to negative 764 newtons, negative because this one's down, plus FB, the force supplied by this point right here. That one's plus, it's going to point up. And then minus Ft, or in this case, the force of tension is actually equal to just the weight of this thing. And all of that has to come up to 0. Our problem is we don't know either this or that, so we can't solve this. But what we can do, well, we could bring in the sum of torques, and we could set up a center of rotation over here, or here, or here, or just about anywhere we want. The only problem is it's going to make it where we have to solve two things at once, because we have this unknown and this unknown. We're after W. We don't care about FB unless we're asked about FB. So here's what I'm going to do. I'm going to put my center of rotation right at the spot where there's a force that I do not care about and do not have. So I'm going to get rid of that unknown force and do my sum of torques. So here we go. Sum of torques about this point, my center of rotation here. I like to start on the left and make my way in. Well, we could say the force of A at, and here's where it gets tricky. That's why we're taking a look at this one. They haven't actually given us any lengths. They have told us the following, that this has a length of L over 2. The whole thing has a length of L, and this is L over 4. This one's also L over 4. Now, I'm going to go ahead and take a look at the force from A, because, I mean, theoretically it's there, but I've got a lever arm that points out like this, dA, and so that has a length of L over 2. Now, I don't know what L is, but I do know that L over 2 is my lever arm, because it goes from here out to here. All right, the thing about this is FA is actually 0, so all of this doesn't matter much. And this would also be sine of 90 degrees. If there were a force at A, which there's not, it would point up. Our lever arm points left, and our force points up, so the angle between them is going to be 90 degrees. So lever arm points that way, force points that way. We have 90 degrees between them. Sine of 90 is 1, but our force is actually 0 because that's what the question is asking. They say when the force at A is 0. Okay. So I'm going to go ahead and put that in, even though the force there is 0, so it doesn't actually apply a torque. Our next one is here. We have that force of tension, 764 newtons, times our lever arm, this one, dt, I guess, but our lever arm right here, which is L over 4. Now, we don't know what L is, but we do know that the lever arm is L over 4. This time, we've got the force down, and our lever arm points to the left. The angle between them is 90 degrees, so we would have sine of 90 degrees. But the sine of 90 degrees is just 1, so we just end up with 764 times L over 4. Now, here comes one of the things we have to keep track of. What I've taught you all in class is think about this force being the only one acting on the object, in this case, the beam. I've got a force down like this. If it's the only one acting on it, it would pull down here, and it would make this thing spin counterclockwise. Now, you can make that whatever sign you'd like, but in my class, we usually use the standard convention. Counterclockwise is positive, while clockwise is negative. Choose one and be consistent with it. All right, here we go. So 764 times L over 4. Let's see, we also have plus FB, the unknown force at B, times our lever arm of 0, Because we have set our center of rotation right where that force is applied. So since our lever arm is 0, this applies no torque. And then finally, we have W times L over 2 times sine of 90 degrees. Our last one is going to be this force here. It's down. And our lever arm, this time, is going to point out like this, to the right. So we've got lever arm, force, 90 degrees between them. And so that's another sine of 90 is 1. Now, big question on this one. If this were the only force acting on it, it's pulling down over here, it would make the whole thing spin clockwise and is therefore a negative torque. Now, these are all of my forces and thereby all of my torques. So, for this to undergo static equilibrium, when I add all of this up, it must equal 0. Well, we've got 0 and that's 0, so if I write this out, I think I get 764 newtons times L over 4 minus the unknown weight times L over 2 equals 0. So here's what I'm going to do. I'm going to add WL over 2 over to the other side. And I get 764 newtons, L over 4 equals WL over 2. And here's what I'm going to do. I want to solve for W, because that's what I'm after. So I'm going to multiply by 2 divided by L. Whatever I do, I've got to do it to the other side too. The L's cancel out, the 2's cancel out, and we're left with just W. Hey, look at that. Our L, the unknown length, cancels out, and we have 2 divided by 4, which is the same thing as 1/2 764 newtons equals our weight. So I can now go through. I remember where my calculator is. There it is. 764 divided by 2 equals 382 newtons. Let me check. 382 newtons is my answer. All right. So this is us applying this. Now, if you don't think to put your center of rotation here and you put it somewhere else, you may be able to go through and solve for things. In fact, if you put it out here, you could solve for the force at point B and then either go back and choose a different center of rotation, do your sum of torques, or if you can find force at B, you could then find W. In fact, with this, we could actually solve for the force at B. However, that's not something that we're actually asked for, so I leave that for a challenge.